Okay, the screen is visible?
Yes, it is visible.
Yeah. Okay. So today's talk would be on integral graphs, Laplacian integral mainly. And before that, I'll tell about co-spectral graphs and graph determined by spectrum. So that just I'll introduce, and then I'll move to Laplacian integral graphs. Okay. So as I told, the outline would be first, I'll tell about graphs determined by spectrum and post-spectral graphs, and then Laplacian integral graphs and some problems which are still open. So a graph is said to be determined by the spectrum if every graph which is co-spectral with G, means which we are starting with, that it's necessarily isomorphic to G. So if I'm getting a graph with the spectrum and there is no other graph which is non-isomorphic to G and with the same spectrum, then we'll say that it's determined by the spectrum. Okay. And if it's not determined by spectrum, then obviously there are co-spectral graphs. So graphs exist with the same spectrum, which are not isomorphic to the graph we have taken. So these are the two things. So either one graph is given, then it will be determined by the spectrum. That means no other graph exists with the same spectrum. And if not, then we have pairs of co-spectral graphs. Co-spectral graph means there are two graphs which are not isomorphic, but they have the same spectrum. Okay, so here we can think about adjacency spectrum or Laplacian spectrum or any other matrix which is associated. Corresponding to that, we can also consider the problem like determined by spectrum or co-spectral. So here I'll basically tell about adjacency first, and then maybe some construction for Laplacian. But the problem, like first thing is like how to determine a graph if it's determined by the spectrum. So to prove that that is a more difficult problem, means this part is a difficult problem, then constructing a co-spectral pair. So of course, like work has been done in these regards. Like there are infinitely many constructions of graphs has been done that with co-spectral pairs or co-spectral graphs, that kind of. But to prove that if some graph is determined by the spectrum, to prove that it's determined by the spectrum, that's more difficult work. So here you can see these are the two graphs. Like earlier, if you go back, the graphs which are getting used in chemical graph theory, they were assuming that all the graphs are determined by spectrum. Means if you have a graph, then its spectrum is whatever you are getting, that is the spectrum for that graph only, they were thinking. And then because if a graph is determined by spectrum, then this problem can be related to isomorphism problem. So that way it was. But nicely, these two examples they got first. And you can see this is a disconnected graph, this is a connected graph. And both have the same spectrum. And here it's disconnected, but if you, these are the two graphs which are with less number of vertices, means 5 vertices. But if you take more vertices, you can get also connected pairs, which are co-spectral, but you can observe that both are not isomorphic. So as I told, this problem is again related to graph isomorphism problem. So this is one of the important problem in graph theory, I mean spectral graph theory. So, and to determine a graph which is to prove that one graph is determined by its spectrum, that is a difficult thing. Like you can observe by this, that path is determined by the adjacent spectrum. And I'll give the proof. So it's not easy kind of, it's a nice observation and interesting. But you can observe that how difficult the thing is. So let us go for a proof for this, that path is determined by the spectrum. For path already, I think you have calculated the eigenvalues. So you know that for the path, you have the eigenvalues this that 2 cos pi I by n plus 1. And these are distinct numbers. So path has n distinct eigenvalue, that also we know because its diameter is n minus 1. So, and you can observe that each number is less than 2. So your spectral radius is less than 2 here. Okay. So for the path, you have n distinct eigenvalues and the spectral radius is less than 2. Now, if I'm thinking that, let's say a path is not determined by the spectrum, that means there is a graph which is co-spectral with this. Okay. Let's say G is a graph and that is co-spectral with Pn. Okay. So we'll show that G is nothing but isomorphic to Pn because we are going to show that Pn is determined by the spectrum. Okay, so I started with a graph and I am assuming that it's co-spectral with Pn. Okay, so if it's co-spectral with Pn, so it will have n eigenvalues. So G must have n vertices. Okay, further, because Ag and Ah, they are sharing the spectrum. So trace of Ag to the power any I is same as trace of Ah to the power, sorry, I wrote here as this is APN. Okay, Pn to the power any I will be same. That trace will be same because eigenvalues are same. So if I put here like trace of Ag square and trace of APN square, so they will be same. And in Ag square, if you see that like diagonal entries, okay, those are nothing but if I take this trace, Ag square trace, that is sum of the like degrees, and that's the number of edges. So the number of edges in your G, that must be equal to the number of edges in your Pn. So Pn has n minus 1 edges. So G must have n minus 1 edges. Okay. So if some graph is getting co-spectral with Pn, then it has n vertices and n minus 1 edges. That's coming directly. And then it cannot contain a cycle because if you take any cycle, then a cycle has 2 as the spectral radius. So if G contains a cycle as a induced subgraph, then using your interlacing theorem, your spectral radius will increase for G. Okay, so it cannot contain cycle as a subgraph. So G has no cycle, so G will become a tree. Then if I think that, let's say G has a vertex of degree 4. So now it's a arbitrary that up to that we reached. Now it has, if it has a vertex of degree 4, let's say, then basically it's containing a star of order 5 as induced subgraph. But star of order 5, if you see, it's a bipartite graph and you can calculate easily that spectral radius is 2. So it cannot contain a star of order 5. That means it cannot contain a vertex of degree 4 or more. And because in that case, spectral radius will be greater than or equal to 2. So then what you are getting, that all the vertices must be of degree 3 or less. Okay. So if I allow now like at least 2 vertices of degree 3, then your graph should contain, like that is already a tree that should contain this type of structure. So you have 2 degree 3 vertices and between them there will be a path. This path length can be small, but at least 2 it will be. Means at least 2 vertices it will contain because you are avoiding star of order 4 or order 5 or more. So it's not like this length cannot be 0. So here there will be one either path of order 2 will be there in between. So the structure would, if I'm allowing at least 2 vertices of degree 3, then you will get this type of subgraph inside the tree. Okay. And if this type of subgraph is there, you can observe that for this tree, 2 is one eigenvalue, because if I choose the eigenvector that I have put here as valuation 1, 1, and all these entries, for these entries you put 2, 2, and then here 1, 1. This way, if you construct the eigenvector, this will give you 2 as one eigenvalue. Okay, so if there is a subgraph of this type of structure in the graph, that means you are allowing two vertices of degree 3. Then you're like you are having a subgraph which has spectral radius 2 or more than 2. So that cannot happen again, because then spectral radius of G will be greater than equal to 2. Okay, so two vertices of degree 3 are not allowed. So then you have the thing that you don't have any vertex of degree greater than 3. And if you are having vertices of degree equal to 3, that will be at most 1. Okay. Now, if I allow, let's say there is a vertex of degree 3, and then all other vertices will be either of degree 1 or 2, that is allowed. So in that case, what I told earlier, that if two graphs are co-spectral, then trace of AG to the power I is same as trace of AH to the power I. Okay. And that means that if diagonal entries, if you are looking for AG to the power I, diagonal entries are nothing but you are taking the closed works of length I, okay, for each vertex. So like diagonal entry, first diagonal entry of AG to the power I, it's nothing but the number of closed works of length I from 1 to 1. Similarly, all the entries are computed. So if I'm looking for trace of this matrix, then this is nothing but the number of closed works of length I from every vertex to itself. So that sum has been calculated, and that should be same because your both the graphs are co-spectral. So this trace is nothing but you are just adding a lambda to the power I, means sum of the eigenvalue power. So that is same for both the graphs. So this trace will be equal to this trace. So then you are getting that if you are taking G, and G is a graph co-spectral with Pn, so number of closed works of length I in G must be same as number of closed works of length I in your Pn, and that is true for any I. Okay. Now, if I check, like if I allow in G one degree 3 vertex, then there will be a subgraph of this form in G. Okay. And your path is like path will be path of order n. So that will contain a subgraph like this. And the rest part of the graph, as you know, that rest part of the graph is containing degree 2 vertices or degree 1 vertices. So if there is a degree 3 vertex, that will be like this, and then you have another path. Okay. And here like you are taking a path, and the rest part also a path, because this the second graph I'm taking a part of a path of order n. So in G you have a situation like this, means you have a subgraph which is a star of order 4, and in path you consider this part of the path. Okay, just take 4 vertices. Now if I calculate the number of closed works of length 4, then the rest part will give me same for both the graphs. But here when I'll calculate, so just calculate the closed works of length 4. So if I want to calculate how many closed works from 1 to 1, so basically I'll go to from 1 I'll go to 3, and then I can come back and again go and again come back. That will give me one closed work of length 4. And then from 1 I can go to 3 and then 4, and then I can come back to 3 and then 1. That will give me another closed work. And from 1 I can go to 3 and then go to 2 and then come back again. So that will give me another closed work. So 3 closed works are there from 1 to 1. And how 1 is the behaving, 4 is also behaving. So like from here onwards there would be, but that will be same for your path, so that I'm not counting. But for this star only I'm counting. So from 1 to 1 you have 3 closed works. Similarly, you can get 4 to like 4 you have 3 closed works. 2 to 2 there will be 3 closed works. Now from 3, if I see 3 to 3, then I can like use this way, that 3 to 4 I'll go and then again come back and then again go and then again come back. This way I'm counting. And then you can also count like 3 to 4 and then come back, and then this way also you can count. I am not counting that one. I'll just count this one. So if you count in this way, 3 to 4 and 4 to 3, like this, if you count, that is 1. And then from here I can go and come back, that is 1. From here I can go and come back like twice that I have to do, that is 1. You have more, you can observe, but I'm counting this much only. So what I counted is, for each one I counted at least 3. Now in path part, if you count, then you can go from 1 to 2 and then come back like this, you can have 1. You can go also 1 to 2 and 2 to 3 and then come back, that will give you 1. These are the two only for 1. Okay. Again for 2, when I'll count, I can go this way, that will give me 1. I can go this way up to 3 and come back twice, that will give me 1. I can go up to 4 and that I can come back, that will give me 1. So here for 2 I'll get 3. Similarly I'll get for 3 I'll get 3, and for 4 I'll get like as I got here for 1 is 2, here for 4 also I'll get 2. So you are getting 2 and then 3, 3 and here 2. So you can observe that when you are counting closed works in the path of order n of length 4, that will be less than this graph, because it's containing a star of order 3, but that should be equal. So this is a contradiction. So that means you cannot have any vertex of degree 3. Okay. So that means all your vertices, because it's a tree and it's with n-1 edges and vertices, so it's a tree. And then you have already proved that there is no vertex of degree 3 or more. So this will be a path. So if you start with any graph and you assume that it's co-spectral with Pn, then you finally concluded that that graph is nothing but a path. Okay, so path is determined by the spectrum. Now you can also prove that the complete graph and all these are also determined by the spectrum, but small graphs, even the very special graph, while proving they're determined by the spectrum, it's not easy. You can observe like P and case. So it's not easy like to determine a class is to prove a class is determined by the spectrum, or certain kind of graphs determined by the spectrum. But if the graph is not determined by the spectrum, as I told, there are pairs of, means there are other graphs which are co-spectral. So we look for co-spectral pairs, kind of. So that then the problem is like you have to construct pairs of co-spectral graphs. So there is a very nice construction given by Schwenk, and that is if you have a co-spectral pair, then you can move for another co-spectral pair, and in finally many co-spectral pairs you can construct. So what is saying that let us start with two co-spectral graphs, and these I am telling about adjacency co-spectral. So if G and H are two co-spectral graphs, and you have two vertices, like one in V, let's say in your G, and V dash in your H. They are there in such a way that if you delete those vertices, then which graphs are coming out, they are also co-spectral. Then you can take any arbitrary graph gamma, okay, and fix a vertex u. And what you'll do, you just make the coalescence. That means attach the graph gamma at the vertex B of G, and attach the graph gamma at the vertex B dash of H. Means you have to consider the vertex U of gamma. So that way, if you make a new graph, means two new graphs, those will also be co-spectral. So here I'll give one example so that you can understand. So I'm taking the first graph G as same as H, okay? And so both are co-spectral because both are same graphs. So G I'm taking as H, and this is the graph, okay? Now I identified one vertex in G, that is V, and another, thinking that it's H, I identified another vertex that is B dash. And you can observe that if I delete V, Okay, from thinking that this is G, and I'm deleting B. Okay, then you are getting a path of order 3 and one graph that is obtained from path of order 6 by adding a pendant here at one end. So these two graphs are coming. Now think it as H and delete the vertex B dash. Then also you are getting a path of order 3 and another graph that is obtained from P6 by adding a pendant. Okay, so G minus B and H minus B dash, they are isomorphic, so they are also co-spectral. So now I can use the whatever the swing construction. So I consider the same graph G and H, but I have identified two vertices B and B dash, and I check that G minus B and H minus B dash, they are isomorphic, so they are co-spectral. So now you take any graph. So here I have taken P3. Okay, and I'm taking the middle vertex that I'll take to attach or make the coalescence operation. So the degree 2 vertex, that is my U. Now I'll form in the well, I'll just attach the here I have attached the P3. So I have drawn in this way, but you can just see that is like you are taking P3 and just attaching the middle vertex with B. So this is the graph. And here the same thing I did for thinking that this is H. So I did the operation here in B test. And you can observe that both the graphs are not isomorphic, but they are co-spectral. Okay, so this is a nice construction. Here I took P3, but you can take any graph. And so this can give infinitely many co-spectral pairs. So this construction not only this is interesting and giving infinitely many pairs, this also has been used to prove this important result that he proved that with respect to the adjacency matrix, almost all trees are not determined by spectrum. Means for almost all trees, you can have co-spectral pairs. Okay, so this is about the co-spectral things. And another nice construction is by Godsil and Meke. So they looked at the matrix of the adjacency matrix, and that obviously it's a general version of the Seidel switching construction that was done for Seidel matrix, and then this is for adjacency matrix. So this switching, they have taken block by the matrices and then they switch the matrix in some some block. So that has been done for adjacency matrix, but you can also apply this for Laplacian and signless Laplacian. So this switching is also nice, and one can think of similar construction also. So here, if you see what he has taken, he has taken N as a 0, 1 matrix, and that is, let's say, of size B cross C. Okay, so dimension B cross. Then he has taken the entries in such a way the column sums they are either 0 or B or B by 2. Okay, so the matrix has B rows and C columns, and the column sums are either 0 or he is putting, that means he is putting 0 columns or all ones columns or half 1 and half zeros. Okay, and if we just in N, if we replace the which columns are containing B by 2 ones, if you replace the opposite way, that means where there is zeros, you put ones, then the new matrix that is constructed is N dash. Okay. So where there is 0, you have to put 1, but you have to do for only the columns where B by 2 ones are there. Okay, so that matrix is N dash. And now choose any B, that is a symmetric matrix with constant row and column sums. If that is symmetric, so if you choose constant row sum, it has also constant column sum. So that kind of B you have to choose. And then C can be any arbitrary symmetric matrix. So then you form two matrices. One is you are taking B, N, and transpose C. And that's again a symmetric matrix. And then M dash you are forming by taking N dash in place of N. So that is already switched some entries have been changed. So then what he proved that these two matrices are co-spectral. And that's easy because you can just construct this matrix that is Q. And if I take this matrix, its inverse is itself. So you can show that M dash is nothing but QM Q. Okay. So these two matrices are co-spectral. So this using this, now taking your like B particular matrix and C kind of like a particular matrix so that it can be adjacency matrix. You can construct two matrices. They correspond to two graphs. They may not be isomorphic, and they will become co-spectral. So I'll give here one example that I have done for Laplacian. For Laplacian, you have to take minus m as L and minus m dash as L dash, maybe the other one. So that way you have to do. So here you can see both the graph G and H. They are co-spectral, and you can observe they are not isomorphic, but they can be obtained from like G can be H can be obtained from G by switching. Here you can observe this part is your N, and on the top block you can think 4 by, like you can take 4 rows, 4 columns accordingly. You can block, you can see the blocks. So you can see the right hand side top block that in your minus LH that has been switched. There were 1 1 and 0 0 that has been taken as 0 0 1 1, like that in the second column also. So the switching has been done in that block. So that way these two graphs can be obtained, and both are non-isomorphic and Laplacian co-spectral. So this technique can be used to construct co-spectral pairs. Okay, and similar observation means students who are listening, they can construct similar type of switching also. And there are it has been done also by many people, and there are other ways also to construct co-spectral graphs. But as I told, the other problem is interesting, that the graph is determined by the spectrum, so it has to be observed first that that is the only graph having that spectrum, and then to prove that is determined by the spectrum. That's interesting and harder problem. So now I'll go to integral graphs, and that I'm going to tell about Laplacian integral only. Obviously, the problem is also for adjacency. So this I want to recall because these operations I'll use. So Laplacian integral graph is a graph whose spectrum contains entirely integers. And the same definition is for adjacency integral. So if the eigenvalues are all integers for the adjacency matrix, then we say that integral graphs. And for Laplacian case, if all Laplacian eigenvalues are integers, we call Laplacian integral graph. Okay, so obviously the first example you can see the complete graph is Laplacian integral because its spectrum is 0 and n. So this is an integral graph, Laplacian integral graph. This is also adjacency integral that also you know. But this Laplacian integral, why I consider it only saying here Laplacian integral part rather than adjacency integral, because this integral spectrum problem is more interesting in Laplacian case. Like if you observe in tree case, the problem is solved. Like in tree case, a tree is Laplacian integral if and only if it is the star, and the spectrum is this. So in tree case, the problem of characterizing all Laplacian integral graphs has been solved already. But in integral case, like adjacency integral, things are because the spectrum is not that way easy to get, and the problem is still unsolved for even tree case. So here another thing is in Laplacian case, there are more graphs which are integral graphs. Okay, so you will get like integral graphs more frequently. So the problems I feel it's interesting to consider the Laplacian spectrum when we are considering integral graphs. Okay. Now, also because I told about the graphs determined by spectrum, you can prove that Kn and the star of order n both are determined by Laplacian spectrum. Okay. Now, one interesting class that is a Laplacian integral class is the co-graph class. So co-graphs, I think you know the definition. So it comes like this. You can start with a singleton vertices, that means K1. K1 itself is a co-graph. Now take the complement of a co-graph, that will be a co-graph. And if you take union of two co-graphs, that is also co-graph. So these co-graphs, they can be constructed starting with singleton vertices. They can be constructed recursively using the union and join operation, or you can think of union and complement operation. But G1 union G2 complement is same as G1 join G2. So basically it's using union and join. So you start with a co-graph and then take the union, that is co-graph. That's a disconnected one basically. And if you want to make a connected one, you have to take its complement, or you think about G1 join G2. Okay. So these co-graphs, they can be constructed from like starting with the singleton vertex and by making union and join, or you can think of union and complement. And co-graphs are Laplacian integral because the way we are constructing, we are starting with K1 and then making union, then join, or you were making union and complement. So in that case, you know that if the one graph is integral, so if you make the union of like two graphs are integral, if you make the union, that will be also integral. And if you make the join, that will also be integral because you know the spectrum, how that look like. So co-graphs are Laplacian integral. Co-graphs also in particular case, they are threshold graphs. They are known as threshold graph. Their threshold graph class is a subclass of co-graph, and that is also a Laplacian integral class. Now, how it has been constructed here, I have given one example. So this is is K1 and this is K1. So K1 union K1. So this is a co-graph. Now, if I make the join, or basically I'm taking the complement of them, G1 join G1 union G1. So, or you can think of K1 union K1, its complement. This is coming as K1 join K1. So this is a co-graph. Now I can take another vertex and make union. This is a co-graph. And I can join again, or you can think of the complement. Okay, so this is again a co-graph. Now I can take another two vertices and make the union. This is a co-graph. And then I'll join, that is a co-graph. So you can observe that when the union is happening, basically you are getting a disconnected co-graph. And the next step you are getting when you have a connected graph, that its last operation has been used as join, or you can think of union and complement. Okay, so I can add one more vertex and then I can join. This is again a co-graph like this. So there are many ways to construct, like as I told, this co-graph class is a Laplacian integral class, and similarly, like many other classes have been observed as Laplacian integral graphs. And if you use operations, like let's say I have two graphs which are Laplacian integral, like G1 and G2. I'll use the union operation or join operation. We know how the spectrum is behaving, so they will also be Laplacian integral. Similarly, graph products can be used also to construct Laplacian integral graphs from the known ones. Many operations has been like used to construct Laplacian integral graphs. But one good strategy that was given by Wasim So is constructing Laplacian integral graphs by adding edges. Okay, so two fundamental operation you can do with a graph is you add one vertex, new vertex with one edge. That is one operation we can do. That is one fundamental operation, and another is if there is some edge is missing, I can put one edge, so I can get another graph. So he means propose this way that given an integral graph, let us add edges and one by one, and let us construct some Laplacian integral graphs. Okay, so this is happening in this way. So before that, I'll define this vector. This is Fourier vector. This is just you are taking the standard vector ei minus ej, I not equal to j. So at ith place you are putting 1, and at jth place you are putting -1. Other entries are 0. This is known as the Fourier vector. Now, if I add one edge to a graph, so let G be a graph on n vertices, and ij are two non-adjacent vertices. Okay. And let's say E is the edge ij. So I'll make the new graph G plus E. That is the graph obtained from G by adding one edge between I and J. So that edge I am taking as E notation. So then the graph G plus E, if you look at its Laplacian matrix, will look like LG plus EIJ transpose. So basically you are putting one S. So one plus one entry corresponding to I vertex will increase in the degree, and corresponding to J vertex also 1 degree will increase. And at IJ and JI place you will put -1. So basically this is the matrix you are adding to LG. Okay. So then, so the Laplacian matrix of the new graph that has been obtained by adding the edge ij has the Laplacian matrix LG plus EIJ into EIJ transpose. And this matrix is, look at the matrix is written as some matrix into transpose. So this is a positive semi-definite matrix you are adding. Okay, and rank 1 matrix. So this, then by interlacing theorem, I think you have read already. So your eigenvalues, they will increase. Okay. So the smallest eigenvalue lambda 1, that is obviously 0. For the new graph also it will be 0. Here the equality will be there. And then your lambda 2g, that will be less than equal to lambda 2g plus c. Lambda 3g, that will be less than equal to lambda 3g plus c. And they will interlace also. They will lie in between like this. Okay. So what you can observe that all the eigenvalues, they are either increasing or remain same. So that way it's happening. And then another thing is, if I look at the sum of the eigenvalues of G plus E, that is nothing but the sum of the diagonal entries, and those are the degrees. So by adding one edge, you basically increase the degree by 2, because you just added one edge. So degree increasing by 2. Okay, total degree. So if I look at the total degree of like G plus E minus the total degree of G, that means summation of all eigenvalues of G plus E minus summation of all eigenvalues of G, that is 2. Total increment is 2. So eigenvalues are increasing, but the total increment is 2. So then we can have the two things we can think of. If we are starting with a Laplacian integral graph G, then G plus E will be Laplacian integral. If these two things happening, n minus 1 eigenvalues of LG and LG plus E, they will remain same, and one eigenvalue will increase by 2. Okay. So then the first graph was Laplacian integral, and G plus E also will become Laplacian integral, because only one eigenvalue that is increasing by 2. Or it may happen that two eigenvalues will increase 1 by 1 each. Okay. So other eigenvalue will remain same. So these two things happening. Then from one Laplacian integral graph, we can go for another Laplacian integral graph. And these two things already we know, these are known as spectral integral variation. So if you have any graph, like I started with Laplacian integral graph because to construct, but for any graph, if you are given with any graph, and it can be a general graph also, like you can take also loop also, and that way the things are done. But here let us consider, like here I forgot to delete this. So let us take simple only. So G be a graph of order n, and Ij are two non-adjacent vertices. Okay. Then we say that the spectral integral variation of G occurs at one place by adding the edge E, if like only one eigenvalue will increase by 2 when we add E to G. Okay. And spectral integral variation occurs at two places if like two eigenvalues are increasing by one each. Okay, so these two are already defined as spectral integral variation because your like one eigenvalue is increasing by one integer. Here, two eigenvalues are increasing by two integers. So that way. And the first case, because this problem I had also considered it. So the first case I'll discuss here. The second case was handled by Steve Kotler. So the here when the spectral integral variation will occur at one place that has been characterized, and this is these three conditions are equivalent. So the spectral integral variation will occur at one place by adding the edge ij when the like degree of I is same as degree of j, means their neighborhood set should be same. Okay, so that will of course imply the degree of sum. But if both the vertices I and j have the same neighborhood set, then it will happen. Okay, and in that case, nicely the eigenvector you will get as the Fourier vector, and the eigenvalue which is increasing basically the di. So the for that graph, di means the degree of I, that is same as degree of j. That will be one eigenvalue, Laplacian eigenvalue for g. And when you are adding that as ij, this di is increasing to di plus 2, and the corresponding eigenvector is the Fourier vector. Okay. So this thing happens. So all these three are equivalent actually. So this is the situation. So if you have a graph and two vertices you have chosen, those two vertices have the same neighborhood set. Okay, they are adjacent to the same vertices. Then if you are putting one edge, then you know that one eigenvalue will increase, and which eigenvalue will increase, that is also you know, that is the degree of I. So that eigenvalue will increase by 2. Okay, like if I have a star of order n, and I'll take two pendant vertices and I'll put one edge. I know that one will increase to 2 and 3. Okay, so there the variation will increase exactly by 2. One eigenvalue will increase. So if you take a star and then just put one edge between two pendant vertices, I can say what is the spectrum. Okay, so 0 will come and 1 will come n minus 3 times, and 3 will come and then n will come. Okay, so this is the complete characterization has been done by Pan. And like considering any particular eigenvalue also you can see, look at the problem. But as I told, the second problem that when the spectral integral variation occurs at two places, this problem was handled by Steve. And he has also characterized the case, but it is not through graphs, so I could not present here. It's looking at the Laplacian matrix structure, you can say how when it will happen. So you can see his paper and you can find out how the characterization has been done. But as I told, both these can be used to construct Laplacian integral graphs from the known ones. And in one paper of Steve, I think he has done entirely characterized using this operation by adding one edge. So what Wasinso had proposed that we can look for Laplacian integral graphs construction using this fundamental operation, that addition of one edge. And what Steve did is he took this operation and entirely, means his paper is, I think, completion of Laplacian integral graphs using adding one edge like that. So there he is entirely characterized, like if you start with a graph and you go on adding edges like this, then you will construct the Laplacian integral graphs. This total construction he has already completely characterized in that paper. So you can see. So this is one way of dealing. Another two important things here I can say, here I wrote this is SG I am taking, or you can think. So this is, let's say G is a graph and your spectrum is given like this. One can question here, which are the graph having n as the Laplacian eigenvalue? Okay, or one can also ask a question, which are the graphs with one as one Laplacian eigenvalue? Okay, the first problem already we had discussed, and n will be one eigenvalue if G complement is disconnected. That means G is a join. This problem is solved. Okay, but the second problem is still open, and this is again interesting. Which graphs are having one as an Laplacian eigenvalue? Now, another thing one can think here that if I am considering Laplacian spectrum as integer spectrum, means all are integer eigenvalues. But I'll ask the question that let us consider the spectrum with distinct integer eigenvalues. So as we observed, our eigenvalues are lying between 0 to n. And if I'm allowing all are integers, so they will take values between 0, 1 up to n. And if I say that they are containing distinct integers, then obviously we have distinct numbers only n plus 1 numbers, 0 to n. So basically we are like allowing all the numbers except 1. Okay. So that is the situation. So if I'm saying that let's say the graphs which are having the spectrum like integer spectrum, also distinct integer spectrum, then we have the chance that means we have the thing that we'll take all the numbers between 0 to n, leaving one number. Okay, so the question was proposed by again the Steve and others that does there exist a graph which will take this spectrum? Means you are leaving I, then I'm denoting this set as SIN. So it's containing all the number except I from 0 to n. So if SIN is this set, whether there is a graph which has the Laplacian spectrum SIN. And if such graph exists, we call that SIN is realizable by a graph, or you can say that it's Laplacian realizable. So given any set of any set S of n numbers, we say that S is Laplacian realizable if there exists a graph with this spectrum S. Okay, so the same question here. So if we are taking the numbers n numbers between 0 to n, so leaving one number basically, so then that is the set SIN. So either a graph which will take SIN as the Laplacian spectrum. Okay. And this problem was handled if your I is not equal to n, then the question is completely solved. So we'll first look at whether such graph exists or not. So if you look for small number of vertices, so if your number of vertices are less than equal to 5, then there are only 5 graphs which are taking such type of spectrum. So the first one is K2. K2 has 2 vertices. Here, if you look at the spectrum, that is 0, 2. Here, 1 is missing. It's taking all numbers, distinct numbers between 0 to 2, and 1 is missing. So this is taking the spectrum as 1, 2. And if I look for P3, that is the graph on 3 vertices, Laplacian spectrum is 0, 1, 3. So this is taking the spectrum S2, 3. Okay, 2 is missing here. And this is a graph on 4 vertices. I think here someone is K2. I mean, this is a typo. So this is a graph on 4 vertices. So you can look for which graph has this eigenvalue. I think here one will be K2. So this has again one graph. This is with spectrum 0, 1, 3, 4. Okay. And so here 2 is missing. So this is S24 it's taking. Similarly, this is the graph K1 union K1 and then join with K1 union K2. This is a graph on 5 vertices. And here you can observe that 1 is missing. So this is the spectrum it is taking. And so these graphs are obtained computationally. You can obtain, or you can just look one by one. These are all 5, your number of vertices are restricted to 5. So these are 2 graphs with 5 vertices. Here 1 is missing, 3 is missing. And this is a graph with 4 vertices. This is the only graph with 3 vertices. This is the only graph with 2 vertices. So these are the graphs which are non-trivial graphs of order up to 5. And these are the 5 graphs which are satisfying that property. But here you can observe that n is missing, you did not get any example. So here like 2 is there, 2 is the number of vertices. Here 3 is the number of vertices, 3 is there. Here 4 is the number of vertices, 4 is there. Here 5 is the number of vertices, 5 is present. Here also 5 is present. So the number which is missing is any other number missing. Okay, so now he considered like they considered this is the paper and these people work together. So they considered all the graphs which are with more than or equal to 6 vertices. And then they proved that G realizes S, sorry, right side is not. Okay, G realizes S1n. So you are just taking out 1 and you are considering 0, 2, 3 up to n. So they prove that G will realize or G has the spectrum this S1n if and only if one of the following things happens. G is constructed in this way. You can observe here, it's the operations are join and union, and most of the time K1 is used. Okay. And the G1 again coming from this graph, G1 realizes this graph. So that has also construction like this. Okay, so the construction is somehow interesting here. So G is K1 union K1 join K1 union G1, where G1 is a graph on n minus 3 vertices, and that realizes this n minus 3 vertices, and it's missing with n minus 4. So if G1 is there, then we can use that G1 and then construct G, which will take S1n. Okay. Or G can be obtained in this way, that G is K1 join H, and H is a graph on n minus 1 vertices, which realizes S n minus 1 S n minus 1. Here your n minus 1 is missing. This graph is with S n minus 1 vertices and the last number is missing. Okay. So these two ways you can construct that will be realized by H1n. But again, this is a recursive construction. If you have such graph, then only you can go for this like this. But anyway, two ways it can be constructed. So it's starting with smaller, we can go for the larger ones. This is for S1n. And for the other ones, like if you consider S n minus 1n, so basically your n minus 1 is missing, then G will realize S n minus 1n if and only if G can be formed in one of the following two ways. G will look like K1 join K1 union G1, where G1 is again a n minus 3 number of vertices graph, and it realizes the spectrum where 2 is missing. Okay. And G or this means this may happen or this may happen. Second case is G is constructed in this way, where H is a graph with n minus 2 vertices, but here the n minus 2 number is missing. So if such graph exists, then only you can go for this construction. If such graph you will get, then you can go for the next step. Okay, so this is, as I told, this is recursive construction, and this is for Sn minus 1n. Earlier I told the first result is for 1n. So for the other numbers like 2 to n minus 2, if I is taking this number, this and then Sin will be realizable, Laplacian realizable, if and only if you will get the graph in this way, that G is K1 join K1 union H star, and H star is a graph on n minus 2 vertices, which is realizing the spectrum Si minus 1 and minus 2. So you are constructing Sin, then you should have a graph which is of n minus 2 vertices where I minus 1 is missing. Okay. So these two results, if you see, one way of construction is this, where you are looking for in this case, like 2 is missing here, and in this case you are taking I minus 1 is missing if you are going for a construction for In. But here the second part is saying that you need one graph where n minus 2 vertices and that is realizing this n minus 2, n minus 2, that means n minus 2 eigenvalue is missing. In the first construction also for S1n, the first case is saying that your n minus 4 is missing in n minus 3 vertices, but the second case is saying n minus 1 vertices and n minus 1 is missing. Okay. Now, like for I, which is less than equal to I is less than equal to n minus 1, then we constructed this way we can get the graphs, right? So here like 1n and then here n minus 1n and then I went for 2 n minus 2n. So last number that I will take, that is n. So if I equal to n, then your spectrum will look like that is SNN, and that will look like 0, 1, 2 up to n minus 1. Okay, so then your question is whether there is a graph that has not been proved. So in your earlier results, so there is there a graph which will have this spectrum. Okay, if such spectrum will be there, then your characteristic polynomial also looks very nice. It's the following factorial basically. So polynomial will look like x into x minus 1 up to x minus n minus 1. Okay, so this is the Pauling factorial, you can say. This comes from the Stirling number of first kind, right? So if such graph exists, means having this spectrum, its characteristic polynomial also will be very nice, and that will look like this. But what the authors they have proposed that this is the first conjecture that SNN is not Laplacian realizable, means there is no graph which will take the eigenvalue 0 to n minus 1. Okay. And they also proposed another conjecture that for each other I, like I from 1 to n minus 1, the set SIN is realizable by a unique graph. And this is depending on this conjecture, because if one can prove this conjecture, then you observe that in all both the theorems, there are two ways of construction. Like here only one way, here two ways of construction. This is one and this is one, and this is depending on SNN. So if there is no graph on SNN, like Sn minus 2, Sn minus 2, so this construction will not give anything for this. So this is the only way you can get. Similarly, for H1n, there are two ways it can be obtained. And first way is here n minus 4 is missing from n minus 3 vertices. But this is n minus 1 number of vertices and n minus 1 missing. Or if the first conjecture is true, this construction cannot be done. So a unique way. So the second conjecture is depending on the first conjecture. Actually, if this is proved, then this is also proved, or one can independently prove this. So this is one nice conjecture and interesting one that is remaining open. So whether there is a graph with eigenvalues 0 to n minus 1. Some developments are done. So in that paper itself, they have proved that the conjecture one is true for graphs with vertices less than equal to 11. You can see the paper. The proofs are very nicely done, and like because it's restricted to 11 vertices, it's not like computationally they calculated. They gave combinatorial argument using eigenvalues, and they proved that there is no graph with the spectrum 0 to n minus 1 if the number of vertices is less than equal to 11. And computationally, this conjecture was handled by Goldberger and Norman, and they proved that after a large number, such graph doesn't exist. So the conjecture is true for large number of vertices. Okay. But anyway, knowing this result will not give anything unless you prove it for the other numbers. So that is important. Once you prove from between 11 to that number, obviously that will also give this. So the developments, those are done. When you are thinking that SNN is Laplace, and let's say SNN, there is a graph and that is realizable by SNN, then basically this spectrum contains 0 to n minus 1. Okay. So 0 to, you can observe that then n cannot be a prime number. because your eigenvalues are 0 to n minus 1. So if you add them, that is basically the degrees. And if you add 0 to n minus 1, that is giving, I think, n into n minus 1 by 2. And that is 2 times the number of edges. So n into n minus 1 should be divisible by 4. So that leads to the second conclusion. Similarly, you can also look for like the product of the non-zero eigenvalues. That is 1 to n minus 1, you will make the product that will give you n minus 1 factorial. And that's the number of spanning trees. Okay. So from that, you can also prove that the number of spanning trees will be n minus 1 factorial divided by n. That must be one integer. So n should divide n minus 1 factorial. That tells that n is not a prime. Okay. So if such graph exists, then n cannot be a prime. As I told, again, 4 is dividing because some of the eigenvalues is and some of the degrees, and some of the eigenvalues is coming as n into n minus 1 by 2. That is the sum of the degrees is 2 times number of edges. So number of edges must be integers. So n into n minus 1 must be divisible by 4. Okay, that tells that n must be congruent to 0 mod 4 or n must be congruent to 1 mod 4. So these two things can be observed easily looking at the eigenvalues. Further, it can be concluded also, you can see the derivation there. You cannot have a pendant vertex, okay? So in that graph, and the smallest degree that will be greater than equal to 2, and the largest degree that will be less than equal to n minus 3. And one nice thing is when some graph is taking SNN as the eigenvalues, then its complement also will take the same eigenvalue. So one can analyze both the things in the complement, and then one can conclude that G and G complement have diameter 3. So you can look for G has diameter 3, and then G complement also will be of diameter 3. So that has been proved by Kinker and others. So G and G complement both has diameter 3. So if such graph exists, so these are the known facts that you can use, that G has diameter 3, G complement has diameter 3, G has those eigenvalues, G complement has those eigenvalues, and also the n number of vertices cannot be a prime, and it's either 4 times something or 4k plus 1, right? 4k minus 1, sorry. So that way the number, and these are the things, those are known. Okay, but still the conjecture is open, and it's a very interesting problem that one can work. Now, another thing that I can connect from here, that is, let's say you are taking these numbers. So I have arranged, put in this way. So you start with 0, and then you put 2 ones, 1 and 1, and then put 3, because I want to make the picture in this way. So you put 2, 2, 2, and then you put 3, 3, and then you put 4. Okay. So all the numbers you take as a set, and that is I'm denoting by S4. So 0 and then 1 is appearing twice, 3 is appearing thrice, and then 2 is appearing thrice, and then 3 is appearing twice, and then 4. Okay, consider that. Okay, this has 9 numbers. So does there exist a graph on 9 vertices which has S4 as the spectrum? Okay, this is a question. And in general, like I can do like this, I'll start with 0 and then 1, 1, then 2, 2, like I can proceed, and last number will be 2n minus 2. Okay, so I can take the set as S2n minus 2. So my numbers will be like this. Okay, so here you can observe that there will be n square numbers. And so can there be a graph on n square vertices that is realizable by Sn minus, that realizes S2n minus 2. So this set is the spectrum for some graph. Does there exist any graph with this spectrum, Laplacian spectrum? Okay, so this is a question. So thing is, if you can prove that there is no graph with such spectrum, then the conjecture of that Steve also can be proved. Okay, so this is a question that you can handle. At least you can try for this one, S4. So you can show whether there is a graph with this spectrum. If there is a graph, you can get the graph, or if there is no graph, you can prove that there is no graph with this spectrum. Okay. So these are the references. Few references already I have given there, and as I told, like you can look for spectral intervariation at two places, Cortland paper. One place you can check for Phan paper, and Wasim So started with that problem, and graphs determined by spectrum, that thing construction I took from this paper, and obviously I followed for certain things Bapasa book. All these many things are there already. Okay, so I'll stop here. Any question you can ask.
Okay, then there is no question. I'll stop recording first.